everyone. Pleasure to see the community growing. Cheers for the organizers, really, really nice. So I'll be talking about mobility by humans and robots. And indeed, it's important for me to tell you about our new lab at Tel Aviv University, the Faculty of Engineering. Lambda stands for AI, machine learning, business and data analytics. And the idea of the lab is to work with real data on real problem, real challenges. And these are some of the companies we've been working with. So it's always, we try to coordinate a group with both people from the university and from the organization. Some of the projects that we've been and actually working right now on are the human mobility pattern that I'll talk about, anomaly detection in semiconductors. We have some guys that we have been working with here, sensor selection, process monitoring, for example, with Applied Materials and Intel. I think that are related to transfer entropy and deep learning, e-commerce, HR analytics, which becomes really a huge subject lately, and so on. So there is a list of topics. What I'll try to do is to talk about the human mobility patterns, and later, if we have time, a little bit about mobile robots and mobility patterns. One thing that I want to mention is this new project that is part of the Lambda Lab, which we call Digital Living 2030. This is a project where, with Stanford University, we try to address some of the challenges of the digital living expected in 10 years from now. And anyone that is interested to learn more, I will be delighted to talk with, including collaboration from the industry. We are very open for that, and we give back. I see so many students that are now part of the industry, so it's a pleasure to see that. So the motivation is clear when we talk about human mobility patterns. It's a multi-billion-dollar industry. We talk about location-based services. We talk about smart cities, smart transportation, homeland security, application health, propagation, and a spread of epidemics, social application, all the Ubers, carpooling, and so on, insurance, and many more. So the motivation is clear. In this research, we got a very unique data set before it was locked by the new regulation that actually described basically the location of people in Tel Aviv and Beersheba for a year on a 20-minute frequency based on their location using the cellular antennas. This is a work that I had the pleasure to work with Shachar, that is here, Shachar Weinstock. It was a pleasure to see that he's here. Where are you, Shachar? So Shachar is here. And Gabi Cohen and Eran Toch, that will be talking later. So the idea was really, instead of just talking about location, was to try and measure what we call lifestyle, which means that when we talk about lifestyle, unlike the most of the applications that look whether people are at the same time at the same location, when you talk about lifestyle, you can relax this assumption. So what you are trying to do is to find what is the lifestyle of people based on their movements. So you can see user one in one location, then in the second location, third location, and back, and you can see another user along the day doing this type of movement. And then using GIS, you understand that these are home areas and work and maybe pub. And although they are not in the same place, you understand that they share something in common. Maybe you can tell something about their age, and they can even be in different cities, and you can tell a lot about their lifestyle. And what we've been doing, beside cleaning the data and working around it, is to create a sort of a distribution where people are spending their time. And you can see this was encoded by those letters A, B, C, and D. And then you can have a sort of a diary, a diary of a person, and you can see how he's spending his time. So A obviously is home, and you see what you see here on the columns. You see the days. We have 3 weeks here, and we have 24 hours as rows, and you can see that he's spending his evening at home and then goes to work in a quite fixed way. This is we call these users working 9 to 5. You can see, for example, that sometimes Fridays is out, sometimes Tuesdays are different, and it's very clear that there is a routine here. And of course, you can multiply it by 1 million users, and you understand that you have a very unique data set here. Now, this is not enough, of course. So you have a good visual, if you want, how people are spending their time. But what you really want, if you want to move to prediction and clustering, is to have a model. And definitely the first model that you would think about is a Markovian model, starting with a simple one. Just if you're in location A, what would be the probability that you'll move to location B? So you can think about a very simple way to take all those users and create those Markovian models that for later I'll show that they are not enough, but for now they are okay. And then if you talk about clustering users, think about those instances of location per user. You can actually create a Markovian model per each user. So you have basically the transition probability. If you are at home, there is I don't know if you see my mouse here, you have a 91% of staying at home and so on. And you can create it per each user. And then you can actually have a distance or pairwise distance matrix between all the users and find how similar they are to each other, based on their movement. So it's not about the location, because we are talking about semantic location: home, work, road, shop. Doesn't matter where it is. And you talk about the similarity here is not only the percentage of time that you spend in each location, but how you move from one location to the other. And then you can use, once you have those similarity matrix, you can always use it. You can use any conventional clustering mechanism. Even k-means can work very well and cluster the users. And one of the things you want eventually to check is that it's homogeneous. So you can take those users or clusters of users and look at couples of location or triples or tuples of larger location and find whether in terms of the entropy they are similar. And this is basically what you get. What you see here is the number of clusters, because we talk about huge amount of people, so you can actually cluster them really. You can, in a city, you can create 70, 80, 100 clusters, and then you can look whether in terms of the entropy within a cluster they are similar to each other. And you have the upper bounds or the lower bound. The lower bound is, of course, if every user is a cluster by itself, so it's very similar to what to itself, and the upper bound is if you cluster all the users together. And in between you see many type of methods, and the one that we proposed actually provides always, not always, but starting from 10, 13 clusters, provide the best homogeneity between the cluster, meaning that people behave similarly in that cluster. And then you can cluster them, but before I do so, I would say that what we found out is that, of course, you are limited by those Markovian models to represent the way that people move in the city. And it's quite obvious, because if you think about even today, there is definitely a dependence of where you were in the morning that will affect not only the next hour, but sometime few hours later. So for example, I went swimming in this morning, meaning that I won't go back to the pool after the conference. Okay, so sometimes it jumps, and of course Markovan models have to be variable in the sense that they can find out when this memory is needed and how to represent those specific locations when you want to cluster people. And this is the second step that we took. So just think about taking a window of the location in 5 hours between 1 p.m. to 5 p.m. And first you run some algorithm based on some extension of the old algorithm of Cho and Liu to find out what is the real dependencies in sequence between those locations. You can find that as long as it's directed acyclic graph, it's okay. And you find out that in this case, the best representation is that hour number 2 affect the location at 1 a.m. and this affects location at 3 p.m. and then both your location at 3 p.m. and 4 p.m. affect your location at 5 p.m. Of course, it's not chronological, but it doesn't matter. This is the best representation of the dependency in the data. But this is not enough. What you need to find out is whether all the places, all the location in time 3 and 4 are really important when you are looking on your location at time 5. So it's not enough to resequence the data. What now you need to do is to find exactly what are the patterns that are important when you describe the location here at time 5, and what are those that are actually the most important when you are about to predict the location at time 5. And this is, and I'm focusing just on this decision tree here, so to speak. But of course, we are talking about huge networks where each part of this network is represented by this, so to speak, decision tree. And this is how it looks when we zoom in. So you have the location at time 5, and you see that for this type of clusters, you have a 25% at time 5, at 5 p.m. to be at home, 65% to be at work, and 10% to be in another place. And since the most important time slot that affect your presence is at time 4, you see that if at time 4 you were at home, then now the distribution of your presence at 5 p.m. changes. If you were at home, there is 80% that at 5 p.m. you'll be also at home. And only 20% that you'll go out somewhere else, and 0% that you'll go back to work. And if at 3 o'clock you were at another place, meaning that at 4 o'clock you went home, but you went from somewhere else, not from work, there is 60% that you'll stay at home, and 30% that suddenly you go back to work. So if you were not at work and suddenly you came home from another place, suddenly there is a slight chance that you'll go back to work. So these type of models are flexible enough to capture the main patterns in the data. And when you do them, you can really now cluster users, and even if there is a presence of noise, you can actually use those models to get a good balance between the variance and the bias of the patterns of the model. And then you can see, for example, a user that we injected some 5 to 7% of noise to his location, and immediately you can indicate that there is a change here. So for example, think about an application that you monitor someone for medical reasons or from homeland security reason, and even if there is some changes in the pattern, although it can keep the same location and the same probability of the location, just the way that he moves between these locations will indicate that there is a change here and you might need to take some action. And when you use it, you can really cluster those many users to different segments, and you know, we did it. So we have the traveling salesman segment, when you see people that are moving around the city in a sort of a more chaotic way. You see the night shift guys that are spending actually their morning at home and then are going out. You see the home sweet home guys, okay, that's spending a lot of time at home, and usually at Tuesday they go sometimes out. You see the student type that go weekends, they go to their parents or I don't know where to have fun. And the nice thing is that when now, in terms of smart cities, you take different neighborhood and you try to find out how the different people in that neighborhood are distributed over the clusters, you see that there is a change between neighborhoods. So, you know, for example, in Lud, there is only 13% of people that are city-focused, okay? While in Kfar Saba, they are around 28%. And again, another example, traveling salesperson, or people that behave like traveling salesperson, as we call them, are 29% in Lod, but only 5%, for example, in Kfar Saba. Maybe because they live 5 minutes from Kfar Saba, as they say. So anyway, so this is a very good fingerprint of a neighborhood. And now think about the application. If you know how people in your neighborhood are living, when they are at home, how do they consume energy? How do they travel around? You can actually create an environment where you provide better services to these neighborhoods. And what we found out, which was interesting, that when you associate it with the socioeconomic score of the Lamas of that neighborhood, you get really a significant result. Meaning, so I'm not talking about causality, but either the socio-demographic feature affect the way that you move, or the other way around, or the way that you move actually affect your socioeconomic situation. But there is a very clear fingerprint of your movement based on your socioeconomic feature or backward. So this is just this portion. So I have 5 more minutes. I'll talk a little bit about this second research that is also about mobility patterns, but talking about all those autonomous cars and robots that will move around the cities. So you will not be surprised to know first that this is not a new idea. Already in late 19th century, people were talking about moving robot. People envisioned that it will look like that. So it's not exactly like that, but people were building actually those robots that were moving according to the light. So this is a very simple robot that moves according to light, and it moves always towards an area that has more light. And actually, if you think about it, when you talk about mobile robots and their movement in the city, and specifically when we talk about searching robot, where you search, and we'll talk about different application, you can think about those lighted area in terms of heat maps. So just think that now instead of light, I'm talking about a big data environment in a city where you have huge amount of inputs like sensors and historical data, temperature, transportation, light control, everything, and you take all of it, you use deep learning, BDIF network, whatever, and you create those heat maps. So here you have an example of a probability map or a heat map of areas that are prone to accidents. Okay, but you can think about many other different examples. You can, of course, if they are prone to accident, you can think about application where you look for, you have those autonomous ambulance that look for area with accident. You talk about, if you talk about those heat maps as representing need for transportation, you can talk about those autonomous Uber car that are moving and they have this target that in 1 minute when you ask for an Uber, they will be there. You can talk about actually those robots moving in pipeline, looking for leakage, in water leakage or sewage. And you can talk about, of course, homeland security. You can talk about other location-based services. So if you have a good view and a good model to capture all those information, and this is part of what we are doing in Lambda based on huge amount of data that we get that are related to smart transportation. You can create a heat map. Then you need to design a scheme where those robots are moving, and I don't have time to go over it, but I would say that you have this probability map, you get new data, you update it, and now, in many cases, since the target is moving, you have to use some Bayesian approach to update the distribution, and now you take an action. So you navigate, you talk about exploration, exploitation. We were talking about it in the last talk. So you move to a new area, you learn something, you update the probability, the target is moving, and in a Bayesian, you all time, in all those schemes, you update the probability and you move around. And when you think about it, we realize that these robots, specifically when we talk about a group of robots, they really resemble, in a way, some of the agents that we know in nature, like ants that are looking for area that have higher probability to contain food, and they indicate they have some simple way of using pheromone to indicate it, to signal each other, and they move around in order to absorb the probabilistic area. And we have also a book about it if you want to learn. And you can apply exactly the same type of concept to those robots. And I'll show you again this small scheme. So you have those, in this case, you have 3 robots, and you have those probabilities where the target is located. And this is actually the real thing that is based on the probability, but is unknown to the agent. And here you have, in the left up corner, the joint probability based on all the signals that each agent is sending to the other. So you have a sort of an overall probability estimate over the area, and this is how you actually control those movements. So again, an application that is based on a huge amount of data, and a way that you actually use it in order to derive some actions, okay? So I'll stop it here, and I don't have time to talk about vehicle information, but something that we do with SafeRide, a startup in this area. I will say that in conclusion, there are a huge amount of new opportunities to analyze large-scale mobility patterns. They often require new models, new metric, new measures. They are very relevant to a lot of application. I didn't talk about drones. We actually bought now a set of drones to the lab. And you can actually apply them to different application and enrich the data with in many different ways. And when you actually combine it with human factors, it even becomes more interesting. So this is some of the collaborators in the second research, and I thank you all, and I can take some questions.
So thank you, Professor Irad Ben-Gal, and we have time for a few questions.
Thank you for this talk. Just a question about is the data publicly available?
So the data is not available, but what we might be able to do is to generate samples based on that data, to simulate data based on that. So we might be able to do that if there is an interest in these type of data sets. Okay? By the way, it's a general. Maybe we have some data sets that are open, but we should discuss it. In general, when the people give their data, they are not prone to share it. Yes?
Thank you for your talk. How did you cluster the signals into the locations A, B, and C?
So it was simply a frequency base. The area where you stayed most was A. So, if you are a workaholic, A is your work. But in most of the cases, A was home. But then we actually, Irad and his students actually combine it with GIS data. But other than that, it's based on frequency. It's a Pareto diagram, yes.
Thank you for your presentation.
Thanks.
Have you tried also density-based clustering?
Yes. I showed one of them. Definitely density-based clustering and distance-based clustering are very good for some of these applications. Absolutely, yes.
Could you just, in 2 sentences, define the CAN activity? What you said, you have no time, just the problem formulation. What are you looking at?
Of the connectivity of...
The CAN, the vehicle.
The vehicle. So this is a complex problem because you have many messages that arrive, and you have also the payload, the actual data. And I must, by the way, contribute a major part of the work to Nadav Costa, my collaborator. And basically what you need to do is first to connect messages that timely appear together. And second, based on those connections, when you reduce dimensionality by TSNE or some other type of method, then model the payloads. And what was done in this case, since the assumption is that you don't know anything about it, can be any vehicle, is to cluster. These payloads are sometimes 16 or larger number of bits. You cluster them to groups. You actually code them by different code words, and you create a sort of a text. And then you apply text and text learning and this type of word-to-vec and many type of applications that are based on text or DNA sequence to those type of words.
Thanks.
Yes.
One last question.
When you build your model, do you use it? When you build your model, do you use as a place like when people go to a school or the university? It's probably a student.
Yes. So in this research again, what the basic research was always only based on frequency, but then Irad talk that maybe is here, and if not, he will come later, is actually enrich them with GIS data to actually know what's going on. And by the way, he also had another research where he took some of the students and tagged them. They don't have any option, we capture them, and he tracked their movement. So it's not like Ant, but what can you do? Yeah, just kidding, of course, Sorry.
Okay, so thank you very much, Professor Ben-Gal.
Thank you.